Albertian Institute of Science and Technology. Make engineers, not just engineering graduates.
Dear students, welcome to the session on circle diagrams of induction motor of the course EE202 Synchronous and Induction Machines from Module 5. I am Ashna Joseph, Assistant Professor, Department of Electrical Engineering, AISAT. This session gives you an insight into the construction of circle diagram of induction motors and thereby determination of the performance parameters. After this session, you will be able to determine the required performance parameters like efficiency, full load current, slip speed, power factor, etc. graphically from the circle diagram. So for a better understanding, I have used a previous year university question asked for May 2019 K2 examination. So straight away into the question. Draw the circle diagram of a 20 HP, 400 volt, 50 Hz, 3-phase star connected induction motor from the following test data. The test data goes like this: no-load test results and blocked rotor test results. From the circle diagram, you are supposed to find the line current and power factor at full load. Given the stator and rotor copper losses are divided equally in the blocked rotor test. This was a question asked for 10 marks, and in the forthcoming session I will explain how the stepwise mark is also awarded during valuation. Moving into the steps. So I have given a steps required prior to the drawing in a series of steps from step 1 to 7 or 8, but there is no need to follow these steps as such. Rather, these things are being given for the ease of understanding. So step 1 goes like this: get I naught and phi naught values from the no-load test. I naught value is from the no-load test data, it is 9 ampere. So I naught, you can write it as 9 amps, and phi naught value from no-load test given a power factor of 0.2. So phi naught value can be obtained as cos inverse of 0.2, which will amount to 78.5 degree. Getting into step 2 is to get the value of ISN and phi s from the blocked rotor test. ISN is a value which corresponds to the normal voltage. While in blocked rotor test, you are getting a 50 ampere, that is denoted as IS. Okay, so this IS corresponds to the value 50 ampere for the reduced voltage 200 volt. ISN instead corresponds to the value of current, short circuit current corresponding to the normal voltage. Normal voltage is nothing but 400 volt. So how to obtain is that ISN is equal to IS into V divided by Vs, where IS is obtained from the blocked rotor test 50 ampere into V, that is rated voltage, again 400 volt, divided by Vs. Vs is nothing but 200 volt, which is obtained from blocked rotor test. All the suffix small s denotes blocked rotor test, that is this 200 is denoted by V suffix s. So ISN amounts to 100 amps. Getting into the step 3 is to find the input power which corresponds to normal voltage, that is WSN. WSN is equal to Ws into V upon Vs the whole squared, where your Ws is given as √3 times Vs Is cos phi s, which is obtained from the blocked rotor test. In some question paper, they will be giving you the value of Ws directly. Instead of the power factor given in this test data, they will be giving you the value of WS directly. Over here, since the power factor data is being given, this formula has to be used. So WS can be found as root 3 times 200 times 200 into 50 into 0.4, which will give you 6928 watts. So this corresponds to the short circuit input power value, which corresponds to the reduced voltage. Now we need to find the value, input power value, which corresponds to the normal voltage. That is WSN over substitution to this equation will, upon computation, will yield us 27,712 watts. So that makes your WSN. Step 4 is to choose current scale, and then we will get into the plotting of circle diagram. Here, for the simplicity, I have chosen my current scale as 10 ampere per centimeter. That is, you can choose any value, say 5 ampere per centimeter can be chosen. It can be chosen as you like. But I have chosen this 10 ampere per centimeter because I need to have a check on my no-load test current. So no-load test current is I0 is 9 ampere. So I have chosen a scale such that it is just matching with this I0 value. You can have a reduced scale like say 12 ampere per centimeter, or whatever scale you can choose as current scale. This is all for the drawing purpose. So now we get into the steps to plot circle diagram. Step A, I have noted step 1 to 8, something like that for the numerical problem, and for the plot of circle diagram I have used step A, step B, like that. So the very first step is to draw the phasor I0 with respect to the voltage V. So before that you need to have an x-axis and a y-axis. Upon the y-axis you will denote V, that is the rated voltage itself. Okay, you will just mark V and x-axis, that's all. So with respect to this voltage axis, you are making all the angle measurements. So I0, we know that I0 is nothing but 9 ampere, and we have chosen the current scale as 10 amps per centimeter. Using that particular idea, your OO dash is a phasor which corresponds to your I0, and that is at an inclination phi naught, and hope you could recall phi naught value as 78.5 degree. So make an orientation of 78.5 degree from this V axis. So this amounts to 78.5 degree, and orient a phasor OO dash that denotes your I0 to the current scale. That is, if our I0 was 10 ampere, then I need to represent my OO dash with simply 1 centimeter. So this 9 ampere means our OO dash phasor is a little lesser than this 1 centimeter. That's all. Getting into step B. Step B is to plot the next phasor ISN with respect to voltage axis at an angle phi s. So from the block rotor test results, we have got your ISN value as 100 amps, and your phi s value is nothing but cos inverse of the block rotor power factor value, which is nothing but 0.4, which will amount to some 66.5 degree. So you can use that 66.5 degree orientation for the new phasor OA, and the length of that new phasor OA is, as per the current scale, we have chosen it as 10 ampere per centimeter, which means to represent your 100 amperes, you require 100 divided by 10, that is 10 centimeter long phasor. So this ISN, that is my OA phasor, if you draw in graph paper, it should be exactly 10 centimeters. So that completes the plot of two phases. One is I0 at an inclination of phi naught with respect to this axis, that is y axis, and ISN at an inclination of phi s, again with respect to V1. So for drawing this particular circle diagram, make sure that you have a protractor with you and take the orientation from this with respect to this y-axis alone. If you take with respect to this x-axis, you will go wrong. Now we get into the step C and D. Step C and D will go together. So what we need to do is, this will go together actually. So you have done till O dash and OA. So from O dash you stretch a horizontal parallel to this x-axis. Okay, so that is my orange line. Now you join O dash and A. Then what you need to do is, you need to bisect this O dash A. That bisection is being done over here. So I have bisected like this using my compasses, and that bisected line is touching the horizontal at the point C. With that C represents the center of the circle. With C as center and CO dash as radius, you have your semicircle, and that completes our circle diagram to an extent. This O dash A is called as an output line. Once you have done till this, you will be getting say out of 10 marks, you will be getting up to 3 or 4 marks. Now we need to have a selection of power scale. For the selection of power scale, what we need to do is, you need to drop a perpendicular from the point A. Always this point A will pass through the circle. Okay, no doubt in that. From point A, you need to drop a perpendicular to touch this x-axis at the point F. Then you need to measure the value AF. So that AF value upon measurement, if you draw perfectly onto scale, it will come as 4 centimeters. This is a complete circle diagram upon computation of the full problem. So we get into the numerical problem steps. So step 5 is to find the power scale. So power scale can be computed both from the numerical values which we have computed earlier and from the graphical one. That is, power scale is computed as WSN upon AF. What is AF? AF is just a measurement from the graph which you have plotted. So AF is nothing but the 4 centimeter which you have got from the graph. WSN already we have computed. It has 27,712 watts. So in effect the power scale will come as 6928 watts per centimeter. Now moving on to step 6. Actually this step 6 is as per the given condition in the question, but for doing the performance parameter which is being asked in this question, we do not require that step 6. Anyway, I am just giving you an overview. That is, this given that the stator and rotor copper losses are equal. You can take this, we have marked AF, and you can take your AE, okay, the point where this perpendicular intersects your horizontal line. So AE represents your total copper loss. This is nothing but your total copper loss. A part of it makes your rotor copper loss and the next part will make your stator copper loss. As per the given question, as per the condition of the question, it is given that the rotor copper loss is equal to the stator copper loss, which means that if AE is say 3 centimeter, 1.5 centimeter corresponds to your rotor copper loss and the next 1.5 centimeter corresponds to your stator copper loss. So over here, as per the graph which is being drawn, AD corresponds to your rotor copper loss and DE corresponds to your stator copper loss. So So this is not required for calculating the performance parameters which is being asked in this particular question, but this division is very important because for you to mark the torque line, this division is at most important. So this division, this D will give you one endpoint of this torque line. So the torque line can be drawn for this particular question, it's not needed, rather I am telling you from O dash you join the line to D to get the torque line. So this completes a circle diagram with respect to the output line and torque line. Now getting into the calculations. So step 6 is over. Now getting into step 7. Step 7 is the one which comes into the question actually. We need to find the operating point with respect to the one in question, not in the point Q, it is in question. So the total motor output as per the question is 20 HP induction motor. 20 HP means while conversion to your SI unit, 20 into 735.5 watts will give you 14,710 watts. So you need to represent the total motor output in the circle diagram. How to represent your total motor output is, you have chosen a power scale previously. The power scale was computed as 6928 watts. So that output power is to be divided with 6928 to get what centimeter is to be plotted in the circle diagram. So the centimeter which we are getting corresponding to the output power is 2.12 centimeter. That I have shown in the circle diagram with the line AT. Moving on to the circle diagram once again. So in the circle diagram, I have noted my AT, which is roughly 2.12 centimeter like this in dotted line. Then from T, you can just have a parallel line corresponding to this output line. So take your roller scale, roll it from the output line and move it, slide it towards this point T, such that from T you can have a parallel, exact parallel to this output line which touches the circle diagram at the point H. So this H is a required operating point as per the question. The question asks you about the full load line current. What you need to find is, your full load line current. That is the first parameter which the question seeks. And the second one is the power factor at full load. So the operating point is nothing but the full load parameters. So in order to get the full load operating point, that is point H, this is a method. So get your output power notated like this. That will give you your point T. From T, you need to have a parallel with respect to this output line which touches your circle diagram at the point H, and this point H is known as the operating point as per the question, that is a full load operating point. Now you need to have your full load current value. How to compute your full load current value is nothing but you measure the value OH. This is your O. So measure OH. So OH upon measurement is nothing but 3 centimeters. OH upon measurement is 3 centimeter. Hope you could recall your current scale. In fact, you need to have your current scale written on the graph where you draw your circle diagram. So current scale is nothing but 10 amps per centimeter, which we have chosen from step 5 or step 4, something like that. So OH is 3 centimeter, which means the current, full load current is nothing but 3 into 10, which is 30 amps. So that completes one answer to the question. The next one is power factor. How to get the power factor is, as I have told you earlier, you need to have all the measurements done with respect to your voltage axis or the y-axis. So you just measure OH, orientation of OH with respect to this y-axis. Upon measurement using your protractor, you will be getting the value as 30 degree. So the power factor is nothing but cos 30. So that is 0.867. 6. So this completes this particular problem. Now I will give you an insight into the mark split up. The mark division goes like this. For the complete plot of circle diagram, you will be getting straight away 5 marks. Then for the computation of the line current, you will be getting 3 marks. That is IFL. When you compute it properly as 30 amps, you will be getting 3 marks. Then for the computation of power factor, you will be getting the rest 2 marks. So that completes a mark split up. Dear students, hope you have understood the session. Thanks for watching.